Hello, I am Dr. Abhishek Joshi and today I will be discussing Bernoulli's binomial uniform Rayleigh and Poisson's distribution. This is the content of the course Digital Communication KEC 601. In our earlier lecture we have discussed about the Gaussian and the normal distribution. So let's start with the Bernoulli's random variable. So what is a Bernoulli's random variable? It is defined as the Bernoulli random variable is a discrete binary valued random variable. So it's having only two values. Binary means 2. So it's having only two values. So binary valued random variable taking values 1 and 0 respectively with a probability. So probability we are defining it as p and 1 minus p. So we have defined the probabilities of 1 as p and the probability for 0 is 1 minus p. So the PMF, or it is also known as the discrete probability density function, is also known as the probability mass function. So the probability mass function for the Bernoulli's random variable having the values, that is for x equals to 1 because it's having the value 1 and 0 respectively. So for 1 we have considered the probability as p, and for the value 0 we are considering the probability as 1 minus p. So the mean and the variance of this random variable is given by the expectation of x. So we, as we know that the expectation of x, where x is a random variable, then this is nothing but the mean, and this is equals to the p. Similarly, the variance of x is equals to p multiplied by 1 minus p. Now let's prove this. Without proving this, we are not able to understand how we are going to get the mean and the variance for this distribution, that is a Bernoulli's random variable and its distribution. Okay. So the function, so we have the function that is the random for a given random variable. We have the probability that is given by p, that is equals to, it is having two values for a value x equals to 0 and for x equals to 1. So for x equals to 0, what we have? We have 1 minus of p. For x equals to 1, so what is the value? It is p. So for discrete, we know that how we can calculate the probability density function. For discrete probability mass function or probability density function, we can calculate the mean, or you can say the expected value of a random variable x using the PDF. Okay, so it is nothing but the summation I from 1, or you can say from minus infinity to plus infinity, and it's a discrete value, so you have to consider all the values, then x of I, p of I, where x is the value of the random variable, pi is the probability for that particular value. So we have the values of the probability for a given value of x, and for x equals to 1 we have p. So probabilities are already given, simply we will expand this and we will solve it. So the expectation of x will give you the mean for the Bernoulli's random variable. So let's solve this. So we are expanding, we are getting x0 p0 plus x1 p1. Now we'll substitute the value. So we have the expectation of x, that is equals to x0. So value is 0 here. So 0 multiply with the probability of at a value 0. So probability is given by 1 minus of p. Similarly, x1 multiply by the probability at the value 1. So we have the value of x1 is 1, probability is p. If we solve it, what we are getting is simply 0 multiplied by any quantity 0, 1 multiplied by p will be simply p. So the mean of the Bernoulli's random variable is simply the p. So we have proved it. Okay, so what we can see here, we have proved this, that is the expected value of the random variable x, that is a Bernoulli's random variable, is p. Now we will solve for the variance. We will solve this one, variance of x, or the variance of the Bernoulli's random variable. Now let us solve it. So we know that the variance, so variance of the Bernoulli's random variable x, we can calculate it simply by expectation of x square minus the mean, or you can say the expectation of x whole square. Okay. So this is how we can use this formula to calculate. So we have the value of the expected value of x, that is p. So this is already solved. So what we have to solve? We have to solve for expectation of x square. Now the expectation of x square for a discrete function, we know that expectation of x square is equals to summation. So we have only two values, so I am simply writing I equals to 0 to 1, then xi square pi. So using the formula we can calculate the expectation of x square. So further expanding it, what we are getting is x0 square pi plus x1 square, and this value is p0, and here the value is 1. So probability for 0 is 1 minus p, probability for p1 is 1, and value for x0 is 0 and for x1 is 1. So substituting the values, what we are getting is expectation of x square, we are getting it as simply 0, p0 is 1 minus p, x1 is value 1, so 1 square will be simply 1, and p1 is p. So what we are getting exactly is simply again p. Now substituting the values of the expected value for x square, expectation of x square in the variance. So while solving, what we are getting, so variance of the Bernoulli's random variable x is equals to, so expectation of x square is simply p, so we are writing p here, minus expected value of x. So what we are getting here, you can see we are getting p, so we are substituting p here, so but we have to take the square, so it is p square. Now we can take p common and we can write it as 1 minus of p. So this is the variance for the Bernoulli's random variable. Okay. Now the next is the binomial random variable. So what is the binomial random variable? So binomial again means it's having the value two values. So the binomial random variable model the sum of an independent Bernoulli's random variable. So we are considering an independent Bernoulli's random variable with a common parameter p, the probability mass function, that is PMF, again because it is a discrete function, so we can call it as the probability mass function of this random variable is given by, so it is given by the probability that x equals to k and k p raised to power k 1 minus p. So this is for the second value, this is for the first value. Okay, the probability for first value multiplied by the probability of second value, that is 1 minus p, or you can consider it as another variable, but again the value will be 1 minus p here. So you can consider either a different variable or you can consider it as 1 minus p, that is a relation between these two. For a value k varies from 0, 1 up to n. So the mean and the variance, because we have considered an independent here, concentrate on this keyword, that is an independent Bernoulli's random variable. So an independent Bernoulli's random variable, the expected value, that is the mean, is simply multiplied by the value or by the factor n. Similarly, for the variance of x for the binomial random variable is simply multiply by the factor n, that is multiply n p 1 minus p. Again you can prove it or you can use the same, it is up to you. So, the example you can take the number of errors when n bits are transmitted over a communication channel, that is the probability of error, we can calculate simply as p. So, we can simply calculate that probability of error as p, and this is for the binomial random variable. Now, the next one is the uniform random variable. So, what is the uniform random variable? First I will explain you what is uniform random variable graphically, then we will consider it. Okay. So, the uniform random variable, it is continuous random variable. So, previously we have discussed about the discrete random variables, okay, Bernoulli random variable. Here this uniform random variable is the continuous random variable. So, for a continuous random variable we are defining it as simply for a limit from a to b, it is having a fixed value and the amplitude is given by 1 upon b minus a. So, this is the PDF, that is a probability density function for a uniform random variable. So, higher value is b and lower value is a, okay, and the amplitude is 1 upon b minus a for a range from a to b. So, where b is greater than a and the interval, that is from a to b, is a range of the random variable. So, the mean for this uniform random variable is given by, the mean of this is given by a plus b by 2, and the variance of the uniform random variable is given by b minus a square by whole square by 12. Now, we will prove these two, the mean and the variance for uniform random variable. Now, let us first prove the expected value for a uniform random variable. Okay. Now, again we know the for a continuous random variable, the expected value we can simply calculate the expected value for the uniform random variable. So, it is a continuous, so we have to take the integration from minus infinity to infinity x f of x, that is a PDF dx. So, the PDF for the uniform random variable we already know, that is equals to 1 upon b minus a. So, here we are calculating, that is from minus infinity to plus infinity x f of x dx, that is equals to the limit is from a to b, and the random variable is x. F of x is PDF, that is a probability density function given by 1 upon b minus a and dx. Now, for integrating for the limit a to b, so integration of x will be, because 1 upon b minus a is constant, so integrating x will get x square by 2. So, we have x square for the lower bound and upper bound a to b, and 2 is constant. So, we are multiplying 2 here. Okay. Now, substituting the limits, what we are getting? While substituting the limit, we are getting as 1 upon 2 b minus a, and this is b square upper limit minus the lower limit. Substituting the lower limit is a square. So, we know that identity, that is b square minus a square, can be written as b plus a and b minus a. So, substituting it as b plus a and b minus a by 2 b minus a. So, b minus a and b minus a will be cancelled out, and what is left is the expected value for the uniform random variable x is given by a plus b or b plus a, whatever you want, you can write a plus b by 2. So, we have proved this, the mean of the uniform random variable is given by a plus b by 2, as you can verify here, a plus b by 2. Now, the variance for the uniform random variable. So, how we calculate the variance? the same formula we are going to use, that is the variance of x is given by the expectation of x square minus the expected value of x whole square. Okay. So, this will be the variance of x. Now, the expectation of x curve, because we know the value of expected value of x, that is a plus b by 2. Now, what we have to calculate? We have to calculate the expected value for x square. Now, the expected value of x square for a continuous random variable x, it can be written as expectation of x square is equals to, since it is continuous, so what we have to write? We have to write the integration from minus infinity to infinity x square, the PDF dx. But the PDF of uniform random variable, we know it is nothing but 1 upon b minus a. Now, substituting the values, so we have to substitute it. So, what we are getting is the limit from, now the limit will reduce from, instead of minus infinity it will be from a to b. So, limit is from a to b, x square, then f of x, the PDF is given by 1 upon b minus a dx. Now, as we know this is a constant term, so we will take it outside. What is left is the integration of x square. Now, the integration of x square is nothing but x cube by 3. So, what we have is 1 upon 3, 3 is constant, so we are taking it outside, b minus a, and integration of x square is x cube, 3 we have already written, limit is from a to b. Now, substituting the limit, what we are getting is b cube minus a cube by 3 times of b minus a. Okay. But we know the identity, the algebraic identity, that is b cube minus a cube can be written as, that is b minus a, I am writing it here, that is b minus a square plus b square plus ab by, we have the term 3 times of b minus a. So, b minus a and b minus a will be cancelled out, and what is left is a square plus b square plus ab by 3. Now, substituting the value of expected value of x square here and the expected value of x in this. So, what we are getting is the variance of x is nothing but, so substituting expected value of x square from this. So, we have a square plus b square plus ab by 3 minus, what is the expected value of x, that is a plus b by 2. So, a plus b by 2 whole square. So, whole square we have to take. So, we have to take a plus b whole square. So, I am directly expanding it, we have to take whole square. So, a square is there. So, I am directly expanding. So, a square plus b square plus 2ab by 2. So, square of 2 will be 4. Now, for the solving it, what we have is, so 4 times of a square plus 4 times of b square plus 4 times ab minus 3 times a square, I am taking the LCM, plus 3 b square plus 6 ab. I am writing it at the corner, then 3 4 12. So, what is left is 4a square minus 3a square, a square, 4b square minus 3b square, b square, and here it is minus, not plus, minus. So, we have 4ab minus 6ab. So what we have simply, final expression I am writing, variance of x is simply b minus a whole square by 12. So we have derived the variance for a uniform random variable, that is equals to b minus a whole square by 12. So we can see in the slide we are getting b minus a whole square by 12. Okay. Now the next is the Rayleigh random variable. So what is the Rayleigh random variable? First I will explain it. The Rayleigh random variable. So Rayleigh random variable, let's consider the random variables x1 and x2 are two Gaussian random variables, each distributed according to the n, that is the distribution having the mean 0 and variance is given by or sigma square. Then the random variable x is equals to under root of x1 square plus x2 square. So is a Rayleigh random variable. The PDF of Rayleigh random variable is given by, so PDF of Rayleigh random variable is given by the probability of x, that is equals to x by sigma square exponential of minus x square by 2 sigma square, where the value of x should be greater than 0. For value less than 0 or equal to 0, the probability will be 0. So this is how we define the Rayleigh random variable. Now the mean and the variance for the Rayleigh random variable, the mean and the variance is given by, the mean of the Rayleigh random variable is given by sigma, the standard deviation, under root of pi by 2, and the variance of the Rayleigh random variable is simply 2 minus pi by 2 sigma square. The same procedure we can follow to find the mean and the variance for Rayleigh random variable, which we have followed to find the Bernoullis random variable, the uniform random variable. The same procedure we can follow to find the mean and the variance for Rayleigh random variable. Next is the Poisson's random variable. So x is said to be a Poisson random variable with parameter if x takes the value 0, 1, 2 up to infinity. So we have the values from 0, 1 up to infinity. So we can define the probability, or you can say the probability density function, which is given by for x equals to k, that is e raised to power minus lambda raised to power k by k factorial, where the value of k is varies from 0, 1, 2 up to infinity. So with pk, so pk, it is equals to the probability that at x equals to k, it follows. So it's always following this condition, always follows in the rule, that is pk minus 1 by pk, that is equals to e raised to power minus lambda raised to power k minus 1 by k minus 1 factorial upon e raised to power k by k factorial. So simply we are getting k by lambda. So the ratio, which we have discussed in previous slide, so ratio pk minus 1 by pk is less than 1, that is for k less than lambda. Then as k increases, pk increases, reaching its maximum. So maximum value we are getting, that is lambda, for k equals to lambda. So when the value, that is lambda less than 1, so the probability pk is maximum for k equals to 0. For the value lambda greater than 1, it is not an integer, then the pk increases as k increases and reaching is maximum for k equals to lambda. If k is an integer, then pk is maximum for k, that is lambda minus 1, and k is equals to lambda. So this is the Poisson distribution. So the Poisson distribution, it is explained as, that is for x equals to 3, we have given an example that you can see the maximum value of this Poisson's distribution is at x equals to 3 here. So at x equals to 3 we have the maximum value, and for probability that as x equals to k we have drawn it, maximum value for this is 0.229 and it is a maximum value out of these 9 values. Okay. So in our today's lecture what we have discussed is the Bernoullis distribution, where we have defined the probabilities as p and 1 minus p, and then we have discussed about the binomial distribution when we are considering n times the Bernoullis random variable. So simply the values are multiplied by n factor, that is n. If it is expected value then it is n times of the probability p, and if it is the variance then the variance is again multiplied, that is n times of p 1 minus p. For a uniform random variable we have defined the mean and the variance, and we have defined the graphically that how it is represented. So it is simply a continuous random variable having the value 1 upon b minus a, the PDF is 1 upon b minus a, and for that we have calculated the mean, that is expected value of x, that is equals to a plus b by 2. Similarly, we have calculated the variance for uniform random variable, that is equals to b minus a whole square by 12, and we have proved in our today's lecture. Then we have defined the Rayleigh's distribution and the Poisson distribution. So here we are going to end our lecture. Thank you.